Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, Guillermo and I speak with Jelena Vučković, professor of electrical engineering at Stanford. She is also the lead at the Nanoscale and Quantum Photonics Lab. In this episode, we dive into the field of quantum engineering. Yelena provides a clear introduction to the various platforms used in quantum technologies, explaining how these systems are modeled and developed. We explore the different branches of quantum engineering, from quantum communication all the way to quantum computing. Given Yelena's expertise in photonics, we dedicate part of the conversation to examining how light can be used as a platform in quantum systems and cover the unique advantages and challenges this approach presents when compared to other quantum platforms. This episode takes us in a slightly different direction from our usual topics, but as you'll hear, the implications for cryptography are significant. Our focus in this episode is on what quantum technologies can make possible in the realm of quantum cryptography, an area we hope to explore further in future episodes. Now, before we kick off, I just want to let you know about ZK Summit 13, which is happening in Toronto on May 12th. ZK Summit is our biannual event where you will learn about the latest in ZK research, the newest applications, and find out who are the most important players in ZK today. It's also a wonderful way to get to know the larger ZK community. So if you've never been to a ZK Summit, I hope you'll join us. To check out the speakers, program, more info about the event, and a link to join, please visit zksummit.com. I've added the link in the show notes. Now, Tanya will share a little bit about this week's sponsor.
You might already know the ZK Jobs Board, a place where teams can share open roles with our community. But when it comes to key hires, finding the right fit in our niche space can be difficult. That's where Missing Link comes in. They're a talent team built for the Web3 era, helping projects across the ecosystem connect with the right candidates at the right time. They've worked with names you'll recognize: Ethereum Foundation, Matter Labs, Lido, Mina, Web3 Foundation, and many more, filling critical roles that drive these teams forward. Whether you're an established project looking to fill a senior leadership role or a startup searching for specialized talent to refine your product market fit, Missing Link can help. They've done it for some of the biggest teams in the space, helping them, and now you, find the right people fast. For more details, check out the show notes and visit their website at missing-link.io. So thanks again, Missing Link. And now, here's our episode.
Today, I'm here with my co-host, Guillermo. Hey, Guillermo.
Hey.
And we are here today with our guest, Jelena Vučković. Welcome to the show, Yelena.
Thanks for inviting me. Hi, Anna. Hi, Guillermo.
So in this episode, we're going to be going in a bit of a different direction than what we usually talk about. We do often talk about circuits on this show, but today we're going to not be talking about circuits in the way we normally do. I'm very excited to get a chance to dig in. Guillermo, you introduced me to Yelena. How do you know each other? Maybe you can give us a little bit of backstory.
So Yelena was the first person I met at Stanford, and also, I guess, the last person to see me out. She was my PhD advisor.
Very nice. Okay, so Yelena, I think it would be great to understand your path into this. I sometimes ask this to cryptographers, but what was the spark that got you interested in the topic that you worked on? Do you remember kind of the moment that started you on this path?
Well, believe it or not, quantum has been around for a very long time. I know it's very popular now, but I was in grad school at Caltech between 96 and end of 2001. And somewhere in the late 90s at Caltech, we started the first project, kind of experimental project focused on building quantum networks for secure long-distance quantum communication, because that's an easier problem to tackle than quantum computing. But this idea of quantum computing and some theoretical work on quantum computing was ongoing there at that time. So that's John Preskill, who is, maybe you heard about him. He actually also is a very important person these days in popularizing quantum computing. Mm-hmm. So I was in grad school there and working on photonics. And then few faculty at Caltech decided to launch this project on building quantum networks. And I think maybe there were only a couple of projects worldwide, in the US, probably all of them back then focused on that. So I started working on that because we were trying to combine this photonic platform that I was working on with atoms that we would put inside of photonics, and then we would build quantum network. So that was the idea. And I was just excited about this whole concept, building something that nobody has ever built, and then you guarantee that if someone is eavesdropping on you and so on. So that was there. Of course, the project was kind of 20 years ahead of time. so we didn't get to build exactly.
Right.
Even today, there are only like 3-node quantum networks, worldwide. And that's what we were trying to build back then. But certainly it launched a lot of exciting efforts. And beyond that, 5-6 years later, like many more projects were launching in that space, and excitement was building up over the next 20 years, right? So that's really when it started, kind of late 90s, which is now a little bit less than 30 years ago, right?
Wow. What about the optics and photonics side of things? Like, was that something that came later, or was that also something you were looking at like right at the start?
Well, I didn't really work on photonics when I was in undergrad. So I'm originally from Serbia, or what was former Yugoslavia back then, and I graduated in electrical engineering and was interested in physics and math, but was kind of looking around into different topics for graduate work. I did some work on error correcting codes at the University of Sydney in Australia after my undergrad. And when I came to Caltech, I thought that that's what I would be doing. That was a time when there was a lot of excitement regarding Reed-Solomon codes, which are used in, I think, CD and DVD recorders. And then...
and now, by the way, used in zero-knowledge proofs, as we talk about in this show.
I have papers on Reed-Solomon codes. Maybe I should...
We'll try to dig some up, add it to the show notes.
Yes.
Cool.
And, there was also some excitement about turbo codes back then. So I came to Caltech thinking that's what I would be doing, right? But then I met my PhD advisor, Axel Scherer. We had some qualifying exam for PhD, and I did really well in physics, although I was planning to do applied math. I mean, I passed it. I did well in information theory too, but then, he invited me to offer me a job in his lab, and I didn't know, I knew about electromagnetism, but I'd never done in my life any photonics or experimental, photonics.
Mm-hmm.
And he told me about this periodic dielectric media, photonic crystals, that they were only theoretically proposed at that time, but his group was the first group trying to make them. And those are structures on chip where you can control flow of light by drilling some holes in 2 dimensions or 3 dimensions. Guillermo knows all about this. He took my class. He did research on this. And, that looked like, wow, he told me one thing that maybe was important in making my decision. He said, you can go anywhere, go back home and, work on math. But, here you have labs where you can make things. Why don't you try to do experiments, right? And I'm like, okay, that's really good advice. Maybe I'll just spend 3 months trying to do experiments, seeing how this whole nanofabrication and photonics
I was about
looks
to
like.
ask, had you ever fabbed anything before? That was the first time you fabbed stuff, I assume.
Yeah, of course. No, that was the first time. And, then at the end of 3 months, I guess 25, 30 years later, I'm still doing that. It was just something that I thought, it will keep me busy. It's interesting, at least for PhD, and then who knows what I'll be doing. But by the time when I was graduating, at the time when I started grad school, we were the only group trying to make photonic crystals. And at the time when I was graduating, everyone wanted to do it. And then it was a good time to get a job. And there was much more excitement both about photonics, and quantum excitement was building up. So I kept doing it. Yeah.
I'm going to do a lot of this, I think, in this episode, but little word checks. Guillermo, you just said you fabbed, or you fab something?
Yeah.
What does that mean?
Like fabricate.
So it's like building something when you say that. It's like creating
yes,
a chip.
nanofabrication.
Okay.
Yeah, exactly. Like, for electronics or for GPUs, NVIDIA designs the chips, but then they fabricate them
Got it.
at TSMC in Taiwan, or, Apple does the same thing. So we do that. We use commercial foundries like, global foundries and so on for some of our silicon photonic chips, but we also make them ourselves. The ones for quantum computing, we make ourselves.
Do you make them in Stanford?
Yeah, at Stanford. Stanford has one of the best university nanofabrication facilities.
Wow.
Actually, it's the first university nanofabrication facility ever started.
Oh, I didn't realize it was the first. I guess it makes sense given Silicon Valley and all, but
Yeah, it was in
Interesting.
1980s. It was started by professors of electrical engineering because, of course, a lot of people doing chip manufacturing
Yep.
around the world, in Taiwan, in the US, actually got education in Stanford Electrical Engineering. So it started by all of these companies donating, I think, tools to electrical engineering.
Oh,
So
okay.
electrical
Very
engineering
cute.
set it up.
Yeah,
But
yeah.
now it's a much bigger facility with many more tools and staff, and our students, and not just students, also people from companies nearby come here to when they want to do some proof of concept fabrication of electronic or photonic circuits. That's what they do at Stanford.
I will say one of my biggest regrets is still not, having done fab something in the fab.
You can
I
do
still
it.
can.
Yeah,
I guess I'm like right here. I should just drive down. Hey, I'll
Just
do it
come
anytime.
back.
Actually, yeah.
Yeah, we always need people who want to do fabrication.
I'll do it. I mean, I'll probably
Yeah, come.
totally screw it up as I normally do, but like that would be fun. That'd be part of the experience.
It's fine. It's okay. It takes some time to ramp up, but yeah, you're welcome. Yeah.
So, Yelena, when we first, or just before we started this interview, I was sort of using the term quantum computer a lot, but you sort of hinted, actually, maybe we should think more quantum technologies. Can you kind of make that distinction for us?
Yes. So quantum technologies is a broader term, and I prefer to talk about quantum technologies because quantum computing is just a subset of quantum technologies. And there are other interesting and more near-term quantum technologies such as quantum sensing, quantum communication or networking, quantum simulation, right? And all of these technologies often share the same devices or components, except that you configure them or connect them in different ways for different applications. And some of them are much easier to scale up or build, right? They're more accessible, such as quantum sensing, where it's enough to have essentially what would be one qubit in a quantum computer to already do some interesting sensing. Or quantum communication, we'll be talking about it later on, but it doesn't really require millions of these quantum bits in order to do something that's already useful, but it's still a very, very useful thing because you can know when someone is eavesdropping on you. So there are a lot of shared elements. Some platforms are maybe a little bit more scaled in the context of quantum computing, like superconducting quantum processors, like the ones that Google is building, but they're not used for communication because they use microwaves, right? And you can send microwaves over long distances, and you would have to cryogenically cool wires and send microwaves. That's, of course, not something that anyone would be doing for scaling, but actually there is something like that at ETH in Zurich. They built 40-meter cryogenically cooled superconducting wires to connect two fridges. But, going forward, people will have to do photonics to connect different, even superconducting quantum processors, and that's called quantum transducers and quantum networks, right? So there are a lot of connections, and even, if a platform is not specifically photonic platform, there is a lot of photonics there. And I like to talk about quantum technologies, again, because of all of these shared elements, and also because something that maybe many people don't realize is that really the main secret sauce behind all of these quantum technologies is what we call quantum entanglement. So just producing independently millions of quantum bits is not enough to do anything useful, right? Because they need to be connected in this special quantum mechanical way, which is what we call quantum entanglement, in order to be truly useful for all of these applications. But entanglement, can vary between 2 quantum bits or few quantum bits to millions of quantum bits, depending on what application you're targeting, right? So the underlying mechanisms are the same, and technologies are often shared, right?
That leads me to a question that I've had, which is, and I was thinking more in the quantum computer context, but I think I could ask it just for quantum technologies. When you look at one of these items or one of these kind of systems, are they often generalized or are they specific? Like, are they meant to do a single thing or are they almost like programmable on some level?
Well, that's an excellent question, right? So if you're looking into quantum simulators, they're kind of what we would call classically like analog computers, right? In classical computing space. So they're made to do one specific thing, right? They're in some case, some simulators can be reconfigured, but generally they're really kind of special purpose computers that are simulating one specific other system, right? And they're not exactly reconfigurable. Basically, you can build photonic system or that simulates another kind of what we call condensed matter physics system, what is happening inside some material, right? But it's simulates particular process, like maybe just superconductivity or something like that, right?
Like the way to think about it is like you have like a modeling problem.
Yes, exactly.
That you are interested in, right? And then, normally the way we think about simulations is like you go and like write a program that simulates that thing. Here, you actually create a device which itself simulates the behavior. So instead of constructing like it's not a general program. It's like this like particular device you've constructed just to perform the simulation of this particular system that you are interested in.
Exactly. For example, you can build hydraulic model of electronic device transistor, right? And, it's a completely different mechanism. There is water there and some other elements, but it's basically modeling the same physics, right? The same thing here. It's the physics of the processes that are modeled on different platforms are the same, but you basically can see what is happening inside of your material by building it out of these elements that are more controllable. But it's then kind of configured to model one specific process, which is what we refer to as quantum simulation. Quantum computing is, by definition, more reconfigurable in a sense that you have all of these gates that you can connect in certain ways and build circuits that would be used to perform different types of algorithms. The way you're doing also in classical computers, right? Because you can write your program and then run different things on that computer, right? And again, it's not kind of completely true that quantum simulators cannot be reconfigured because there's something called reconfigurable programmable quantum simulators, right? But in general, this is how the systems are distinguished, right? So it's not like gate-based system.
So you've mentioned entanglement, I think twice now. And
yes.
Is that the big distinction between classical computing and like how we think of binary 0-1 energy on off? Like, is that the part where it works very, very differently? Like, maybe we should talk a little bit about what entanglement is.
Yeah. So if you just look at the qubit level, right? Qubit versus bit can be in states 0 or 1. Qubit can be in superposition states of 0 and 1. And that's what people often emphasize. Oh, there is this superposition of 0 and 1. And then kind of I put everything in a superposition and that's why it runs faster. That's not true. Like for quantum computer, I'm just saying there is a superposition, but that's not the main ingredient. The fact that you can put millions of independent qubits in superposition is not going to bring you anywhere. You need to also build up this entanglement. Sometimes the algorithm itself produces some entanglement by interactions. That's sort of what happens in Shor's algorithm and some other algorithms. Sometimes you produce all of this entanglement and you use it for sensing or for networking or for some sort of simulation or computing. But that entanglement is the main ingredient. That's what distinguishes it completely from classical systems. So what is entanglement? Entanglement is, we sometimes refer it to as non-classical correlations. You know what correlations are. Things can be correlated. You have a process where, for example, I always produce two coins. I put them always heads up or heads down, right? So then I do that, and then you know that outcomes are always correlated because I put them that way. But quantum correlations or entanglement is different, and that's also, you may have heard about Einstein calling quantum mechanics spooky action at the distance. There were papers and arguments between Einstein, Podolsky, Rosen.
I didn't hear what you said there, though. What did Einstein say?
Einstein was referring to quantum entanglement as spooky action at a distance.
Spooky action at a distance?
Yes.
He
Okay.
basically used quantum mechanical entanglement as the argument that something must be wrong with quantum mechanics theory, right?
Oh.
It is so counterintuitive that it was confusing even the best physicists of the time, right?
Huh.
And many physicists afterwards. And of course, later on, it was, of course, proven that quantum entanglement is real and it's very different from classical correlations, which what Einstein was referring as some hidden variables and so on. So I haven't explained what it is. I'll tell you now, right? I'm
Okay,
just
cool.
saying it is very counterintuitive because we don't have anything like that in classical systems. But it is the main ingredient for all quantum technologies. And
Okay.
this is why it's also very hard to scale them up because quantum entanglement generally is very fragile. When quantum mechanical objects interact with their environment, they lose this, entanglement, quantum mechanical properties. And that's why this is exactly hard to build and scale up, right? For making even more practical technologies. So quantum entanglement, again, these are correlations, non-classical correlations, quantum correlations that only exist in quantum mechanical world.
And it's between what? It's between like two
It's
different...
between objects,
Okay.
between the objects, between two or millions of different objects, right? And they guarantee that if you are measuring the state of one object, you would know automatically what the state of the other object would be, no matter where it is.
Interesting. And is it always the same or could it be like a different state?
It could be different depending on the outcome of your measurement. You are setting up something that may be thousands of miles away from you in a
Wow.
particular state that you would know even without looking at it. And that's really, kind of already gives you a hint of how this potentially could be useful for cryptography, right? Or quantum key
Yeah.
distribution, because if you're distributing these entangled states between different parties, and, let's say between you and Guillermo and me, and we're not at the same place, but we all hold some objects that are entangled to each other, and I perform measurement, and I measure 0, for example, I know that right away that you and Guillermo would also have zeros, right?
Okay.
Even if you don't call me up and tell me that, I know that you would have it, right? And if I measure 1, I know that you would have ones as well. Of course, someone may eavesdrop and mess that up. And I would also, from these algorithms know that someone has eavesdropped because there are some parts of this algorithm that assure me that no one has eavesdropped or someone has eavesdropped. So we can repeat the process until we are sure that eavesdropping is not happening. But again, I think that's an example how entanglement can be useful for cryptography. But then similarly, it could be useful for sensing and computing and so on. Yeah.
Maybe here's an analog for the eavesdropping part does no classical analog, but entanglement has a little bit of a very dumb classical analog. And it's like, imagine I just pull 2 cards from a deck, like the ace and the king, right? And I shuffle them, right? And then I give one to Yelena and one to you, Anna. The second that you turn one of the cards around, you immediately know what the other person has because there's only 2 possible cards, right? So in some sense, this is that's the classical analog of it. What is crazy and what is deeply annoying is actually the quantum case also is distinguished by this fact that Yelena was mentioning, which is you can know that somebody is eavesdropping because the act of measuring itself will change the statistics that you get.
Exactly.
Schrodinger's cat.
Yeah, exactly, like that. Exactly. It's crazy, right? You can literally find out someone's eavesdropping because it is impossible to measure the system without destroying it in some way.
Wow.
And that's the real big change here too.
Crazy.
There's other kinds of correlations that we're not specifying here, of course. So
yeah, so we're distributing these entangled particles between 3 of us, and we're doing our measurements, and we're getting and we're not comparing anything, but to find at the end of the day, let's say we distributed millions of these particles between us, and usually that's done using photons because they can travel longer distances. Then we call each other and we take some subset of those bits that we distributed and measured. And, first we have to compare how we measured them and so on. But it's okay. We're not revealing information there. I'm not going to go into details of that. But just on the eavesdropping, we can kind of sacrifice some subset of them. Let's say, 100 of these bits that we measured, and we compare them, right? And assuming we measure them the same way, because in all of these protocols, maybe kind of how you are measuring, that's part of the protocol. But assuming we kind of set up our measurement equipment in the same way, quantum mechanics guarantees that we should be seeing the same bits, right? We should all be seeing like zeros or ones and so on. If we're not seeing the same bits, then we know, that someone was eavesdropping, basically.
By the way, extremely analogous to the way ZK proofs work.
Okay.
Right. Like specifically, think about it this way. When somebody goes and measures let's say somebody is eavesdropping between the two of you. I'm eavesdropping between the two of you.
Mm-hmm.
Sorry. And when I do these measurements, the state of these individual bits that have been transferred, essentially, you can think about it as they become uniformly random. So when you pick a random subset of 100 of these qubits and then compare them against each other, right? The probability that I get lucky and both of those are exactly identical is 2 to the negative 100. For the same reason that the ZK proof has the same thing where you do a test repeatedly until you're sure that the statistics work out. Right? It's exactly the same idea.
Okay.
Exactly the same idea. Exactly. Yep. I didn't know. I mean, I'm learning here about ZK proofs, right? And I'm glad to have you as a translator here.
It's pretty fun. I don't know.
Yeah, Guillermo, you
like
speak
this.
both languages. It's so cool.
I know. I'm a secret underground physicist. I'm not really a physicist. I mostly did math, but I still like to pretend. So it's fun.
Well, you were still exposed to enough physics. Yes.
That's true.
I have another question about a word that you've been using, which I feel like maybe I should have asked earlier, but even qubit. What is a qubit?
Mm-hmm. Yes. So qubits are short for quantum mechanical bit, right? So that's this kind of elementary object that we use in quantum technologies or quantum computing. So in classical computing, there are streams of zeros and ones. Mm-hmm. So bit is 0 or 1, right? And switch can be placed in the state 0 or 1. Transistors can be zeros or ones. That's how we do all of the classical information processing. And even before that, there were you can do it with mechanical switches, with anything that has two states, right? There were other platforms that people were using for computing, like vacuum tubes, switches, and so on, mechanical switches. In quantum computing, this elementary, piece of any quantum technologies that we are using is a quantum bit. Mm-hmm. And quantum bit can be in a superposition of 0 and 1, right? That can be mapped to different platforms. Like in classical computing, you can map bits to different platforms, from mechanical switches to electrical switches. We can map quantum bits to different platforms. Maybe easiest one to grasp is light, right? Mm-hmm. Because if you map 0 to presence of one particle of light, which we call photon, in, let's say, one channel, right, which is some fiber, right, or guide for light, something like that, and you map 1 to presence of a photon in this other guide, then you can also put that same photon into a superposition of being in one or the other guide, right? And that's called quantum bit. The other way of mapping it would be photon, what we call polarized. We all know people wear polarization glasses, right? There may be different polarization of light, which is essentially how electric field and light is electromagnetic field oscillates. So you can put 0 in what we call horizontal polarization. You can put 1 in vertical polarization. But then, of course, your photon can be polarized anywhere between 0, like horizontal and vertical, and that would be a superposition state, right? And those are all possible ways of mapping qubits to physical implementation. They could also be microwave current. It could be also state of some, device, electrical device. I mean, there are many different platforms that people are pursuing. My group, for example, is also pursuing states of spins, right, of electrons inside of some solids. And particle can be in different spin states, which we map to zeros and ones, or superposition of spin states. So again, these are just very different physical implementations, right? It could be presence of atoms somewhere, absence of atoms somewhere, many, many different things. And that's what you may hear about in the media as all of these different approaches to quantum technologies. Someone is talking about superconducting circuits, photonics, spins, ions, atoms. There are many, many different flavors, but those are just different systems into which they can map, right?
Interesting. And some of these almost sound like platforms or techniques or something that's happening.
Yes.
And some of these sound like objects, like I know they're not exactly, but like photon or atom. Like, so I am...
Photons are objects.
Okay.
Yeah. So, I mean, that's, again, going deeper into quantum mechanics. I know it's a little bit counterintuitive because we think about light as wave, right? But then photons are indivisible particles of light. And the basic principle of quantum mechanics is wave-particle duality, that everything is at the same time both wave and a particle. Actually, we think about atoms as objects, particles, but atoms also, since they are quantum mechanical, I mean, they're also waves. And, even bigger objects can be both waves and particles. But of course, the bigger they get, the easier for them is to interfere with the environment. So you kind of lose the effects of maybe their wave properties, right?
Interesting.
Yes, but that maybe, thinking about them as both waves and particles is very, very important to grasp that superposition, because probably for you it was not confusing when I was talking about polarization of a photon being in superposition of horizontal and vertical, because that just means rotating polarizers in your glasses in a certain way. But then it's probably very counterintuitive for you that an electron can be simultaneously in two different states, right? How can it be? Because it's an object. Can a tennis ball be simultaneously in two different states? Can a cat be dead and alive, and so on, right?
Yeah.
I mean, but when you think about objects as waves, then it's not counterintuitive anymore.
Yeah, exactly. I'll distinguish two things early on, right? There's like the qubit is like much the same way as a bit, is an idealized model of like let's like think about it as like some like basic like object that we like to study. A bit isn't a real thing, right? Like a bit has to be created by something. In the case of, RAM, it is like generated by like the existence of like a literal like atom in a cavity, or a literal electron in a place and not, right? In the case of, NAND memory, you like created via these latches. But like a bit, right, is like an idealized thing that we say like, cool, a bit like exists. A bit has to exist in like the real world for us to be able to use it. Like we have to have like bits are in memory.
But we could create them in all sorts of ways.
Exactly. But there's many physical manifestations of that. The same thing is true of a qubit here, which is what Yelena is getting at, right? Like,
yes.
Not only that, like there's also idealizations, not just of like, systems, but there's also idealizations of wires here too. Like, how do you communicate different states across different bits, right? Like, in the standard sense, you can think of like, you can create a computer with water. Like, you can actually, there's like this cool, sick Soviet machine at some point that was created in like the 60s that like somebody essentially created a computer with water that could add and subtract and do all sorts of stuff. And in that case, like the wire is a literal pipe carrying literal water, right? So that's the way we transfer bits from one place to the other. And similarly, you can think of, there's many ways of transferring kind of states or information between two, qubits, right? And setting up all sorts of like crazy things. Number one is you could have a fiber optic cable, which like transfers light. Number two is you could have a superconducting wire that transfers like certain microwaves. So it's just like taking it's thinking about two levels of abstraction, which is the bit or the qubit as the like, this is like a thing that like is completely an idealized model, but is a very useful one because it can break down a lot of steps. And then mapping it down to the reality, which is like what Yelena does, which is like, how do you, okay, cool. Like, yeah, very, very cool, like nice mathematical model you have here. Now make it real, And so I think that's where really like where things get crazy.
Exactly. And then, speaking a little bit beyond that, you can kind of map these qubits to different platforms, photons or particles, like spins of particles or currents and so on. But then to really get that main engine behind all of these quantum technologies, which is quantum mechanical entanglement, it turns out you need to interact them somehow, right? And there are sometimes processes that happen when you're generating them. You can produce entangled photons using certain processes, and they're entangled right away. Sometimes you produce kind of individual photons first using some processes, and then you can interact them somehow, interfere them, and build entanglement. But that part is really what is the hardest part. Producing millions of independent qubits is easy, but then making it in millions of entangled qubits is hard, right? And that's really why the progress is so slow. Right.
I'm so happy that listing of those techniques, I don't know what you call these, but like, or forms, or like, I liked that list. What it made me think, though, is when you saw that, like those announcements from Google, like what are they doing? Like what is the exact technique that they're playing with? Like what is the exact like object that they're using?
Yes. So Google is primarily pursuing superconducting platform, right? So these are superconducting systems. So as Guillermo was saying, there are these superconducting wires and some superconducting elements, gates that they are using that can be in different states, right? Which are in some way kind of similar in physics to the platforms that people are using with atoms, or people in my group are using with some, impurities in semiconductors, because these are objects that can be viewed as some quantum mechanical oscillators that can have different states, right? So it's really like that. But they're physically very different because they're made lithographically and they're made out of superconductors.
Lithographically.
And the initial platform was these Josephson junctions, where basically you can produce some oscillations by building superconducting systems, but then they've evolved into different types of superconducting qubits. And that's really their qubit, right? This superconducting element.
What is the material exactly?
People are using different types of superconductors for this. That's why they're different kinds and different systems. I'm not 100% sure what Google is using. Maybe niobium. That's the one that many people are using.
Element.
But that's, So superconductors are materials that basically don't show resistance. They don't, when you flow current inside of them. But that generally happens at very low temperatures, which is why when you see Google announcements, you see these chandeliers which are open and chip, right? That chandelier is inside of the dilution refrigerator. We use dilution refrigerators to cool systems to very low temperatures, close to absolute zero. And depending on which material is used, the experiments have to be done at low temperature, where the system is superconducting, for example, right? Because at higher temperature, it wouldn't be superconducting. But, all the other systems are also cooled in different ways, right? Even all photonic systems are cooled because they use superconducting detectors, which also have to operate at very low temperature, or systems based on impurities in diamond and silicon carbide that my group is using also have to be cooled, not to millikelvin, but few Kelvin temperatures. So pretty close to absolute zero. And atomic physics systems are also cooled, but they're not cooled in fridges. They're cooled with other lasers because you have to cool them in order to suppress basically their interaction with the environment and preserve quantum mechanical properties that are very fragile. Yeah,
it's insane. Like, yes, you can cool things with lasers. Like, we've just this is going to sound like magic to pretty much everybody on the show, which is very fun to me. But really quickly, I think it would be also very useful to describe, actually, like, just at a very high level, like, you say like, oh, we have these imperfections in like a material and we can use those at, what do you mean? Like, what does it mean to like just from just a high level perspective, like, what does it mean? Like, how, when you have to build this thing, you go into the fab, like I give you like, a slab of some material.
So the imperfections that I'm talking about that we are using in my group to build these quantum systems are what we call impurities. Some people call them defects. They're intentional defects in diamond and in silicon carbide. Those are two materials that we use. And these are leading platforms for quantum sensors like magnetometers. There are also companies developing that now. And also they've been used in state-of-the-art quantum networks. We didn't talk about this, but, quantum communication uses photons. If you want to do this secure quantum communication over distances beyond maybe 50, 100 kilometers, where you start incurring losses in fibers, then you have to build something called quantum repeater. You have to distribute quantum entanglement to larger distances using something that lasts longer than photons, and that's where you use these impurities in these materials. So what is it, right?
Yeah.
So there is a
Yeah, think about it. Like you put on your bunny suit, you open the door, you come in with a thing. What do you do?
Yeah, so let me explain you what it is, right? So what color is diamond, right? That's one of the materials that we use.
Clear.
Clear, exactly. But you can buy diamond jewelry in different colors, right? Like purple, red, and so on. Where is that coming from? It's still diamond. It comes from defects, impurities.
Interesting.
Because people load, what is ruby? Ruby is sapphire. Sapphire is clear, but ruby is sapphire, which is filled up with chromium inside of it. And the color comes from these impurities.
Okay.
So we work with impurities in diamond. We use tin vacancy in diamond, and we also use silicon vacancy in silicon carbide, which is basically another material using in jewelry, fake diamond jewelry, because it's much cheaper than diamond. It's also used in power electronics, electric cars, and so on. But when you see these materials like diamond, you said, Anna, it's clear, right? But when you put impurities, it can change color because these impurities can generate light at specific wavelengths, right, at specific colors. But they also behave like atoms, individual atoms that are trapped inside of this material. So we don't need to trap them in vacuum, as people are doing in atomic physics and in some approaches to quantum computing. We can actually still control them with microwaves or with light and use them as qubits, right?
Interesting.
So when you look at our chips, they still look clear because there are qubits there, but they're in much lower concentrations than concentrations of chromium in ruby or, other impurities, chromium in or nitrogen in purple diamond, right? You can buy purple diamond, which is filled up, loaded with nitrogen, while the environment is carbon. No, our chips still look clear, but they have qubits. So these are intentionally inserted impurities at certain places. And you can do that intentionally. You can control position. We collaborate with Sandia National Labs or putting them where we want. And then we can also take these chips and then make structures inside of it that would guide light, that would control these qubits.
Oh, wow.
Or guide microwaves. So we go into the lab, we take the chip, we use exactly the same tools that people would use to make microprocessors, right? I mean, the same machines, doing some lithography, drawing the pattern, bombarding with some plasma ions to etch, to drill holes, putting into some chemicals to etch more, when you see people in bunny suits. And that kind of makes these structures that would actually guide light or microwaves, which produce interactions between qubits.
Interesting. In doing research for this, I saw a few graphics of this, I believe. But maybe for the listener, it'd be useful to describe what that actually looks like. What does the graphic show? What are you doing?
Looks like abstract painting. Yeah, probably, right?
Yeah.
So if you think about this, so maybe Guillermo, maybe the easiest way to start, Guillermo was talking about microfluidic models of computers, right? People can make them, right? There is a microfluidic transistor even model. So if you're thinking about water, right, you can think about water, right, river, and then it can branch into two different branches. And half of water goes one way, half of water goes the other way. They can recombine, but you are using, basically, you are guiding water down the river flow, right? And it can go in different branches, split it out, and so on. With light or with electricity, we can guide kind of electrons, current, using wires, right? If you open any device, you see a lot of wires. Those wires are guiding current, right? They're guiding it from plants, whatever power plants you have, all the way to your home, to your device, and so on. And they're basically guiding current to all of the different devices that you have in all of your appliances in order to control some of these switches and transistors that are acting there as bits, right? Like even inside of these computers. You can do the same thing for light, right? But you need to guide it, right? So one thing that people are familiar with are optical fibers that are guiding light over long distances, which are just very, very long threads of glass, right? But if you would really like to do some processing on the chip, right, which is like piece of silicon or diamond or silicon carbide, then you need to produce these flows for light that are bringing light in different parts of the chip and making it interact with these qubits and collecting light and processing it. So you can just think of it as kind of carving this material in such a way that you can flow light, right? Which you can kind of see it by analogy with water because it's waves.
But are you activating the qubits with the light, or are you like...
Yeah, exactly.
Okay.
So we're controlling qubits exactly with light and electromagnetic waves, right? Because for us, qubits, specifically in the platform that I'm using, qubits are these kind of states of spins of some particles that are next to the impurities. I told you really want to build entanglement, right? And you can build entanglement only if you make them interact. So we make them interact by guiding light and making them interact by kind of all being reached out by the same kind of flow of light, right?
But is information brought around? I'm thinking not here, but is there any information that's moving with the photon, or is it just like turning on?
Photons, yes, exactly. Information is moving with photons, right? And photons are... you may have heard that people are sometimes talking about stationary, particularly in the context of quantum communication, quantum networking, stationary and flying qubits. Photons themselves are also qubits, right? Because I was telling you how you can put them in superposition of different states. And photons are wonderful because they can travel very long distances. The problem with photons is they don't interact strongly, right? I mean, lightsaber, right? You know, we know like when you hit photons from two lightsabers, they're kind of looks like they're interacting, right? But in reality, if you just take two laser pointers, they would just pass through each other, right? Lightsabers don't exist. I mean, we know photons interact, but they interact very weakly. They don't, unfortunately, they don't interact as strongly as they do in lightsabers. I wish they do, right? And that means that first, they don't interact very strongly. And second, they kind of easily leak out into the environment. They're not very long-lived. So we still use them as these flying qubits to make other things interact, to transmit information between different processors, like superconducting processors or different spin qubits, like what we're using, or different atoms. But we use something more long-lived as a qubit itself, like memory, so that we have more time to do all the different operations. Is that making sense?
A little bit. So, like, you sort of talked about the different, I want to say, like, types, the spins, the microwaves.
Yes.
But do those different states talk to each other, or are you sometimes using all of those at the same time, or are you usually focused on one and they're only talking to those in the similar context?
Yes. So sometimes you are using multiple platforms for multiple things. I mean, there are, again, different approaches. There are also approaches that are based only on photons. But considering that photons don't kind of preserve quantum mechanical states for very long, generally those approaches are based on the fact that you try to produce some larger entangled state, and then you repeat that many times, right? It's like happening, decohering very fast, but then maybe you try to do everything very fast, and then you can kind of map it to certain types of algorithms. I mean, it hasn't been scaled that well yet, but that's kind of the underlying principle there. And you need to suppress all the inefficiencies in your system as well as you can. Platforms that I'm working on, I mean, most of the time is just this impurities that are interconnected with photons and then microwaves, and that's what is there.
Yeah.
But then Google works on superconducting processors, but in order to connect different superconducting processors, they have to somehow convert their microwaves, and that's a very different part of electromagnetic spectrum. That's what you have, what your phone uses, or what you have in your microwave oven, very different from light, but again, electromagnetic wave. That has to map efficiently to optical waves that you can transfer over long distances. And that's what we called quantum transducer. And to produce quantum transducer, you would use some of the photonic technologies that we use and then connect two of their fridges efficiently. So that system would have superconducting platform plus photonics plus some of these impurities in diamond or silicon carbide or something else that can also act as a transducer, right? So there are a lot of things that are put together at the same time.
Interesting. In the work that you do, are you primarily modeling this and looking at what it would do, or are you actually physically building this thing? Like you mentioned the fab, so it sounds like you're actually building it, but like
building, okay, and modeling.
Because this has sort of been my question about like the quantum generally, like the field, like how much of it is people using materials and like doing the thing that they say they're doing, and how much of it is like a theoretical, like this is what would happen if.
Oh, yeah, definitely. Both are happening and both are super important because there is a lot of effort in trying to find other, quantum algorithms that would often also offer exponential advantage, like Shor's algorithm, which is very fast factoring algorithm, would offer, right? So that's really one of the burning questions in the field. How do you map this efficiently to other kind of broadly useful problems, not just modeling physical systems, not just doing, physical discovery in physics is important, but I don't know, modeling black hole may not be so important for broad community. Maybe if you can do some very fast optimization of markets or something, that's much more important. And clearly, Shor's algorithm is important, right? Because if someone can break all modern cryptography, then that with a quantum computer, of course, we care about it, right? And that's an important problem. So there is a lot of work on quantum information theory, on the theoretical basis of this, and it's a very important work. There is also a lot of important work on verification of quantum computers, because, if you build a machine that is doing something that no classical machine can do, how do you even know that it's doing something correctly?
Totally.
Right? And that's a very important question. So there is a big community working on the verification problems.
Yes.
And, we're already, even in the systems that my group is working with, where we have about 10 qubits in a resonator that are simulating something, we're already running into problems that, we can't scale this up. It's already very hard to classically simulate. So we collaborate with a group in Munich that is doing this on supercomputers, simulating what this tiny thing is doing in the lab, right?
Interesting.
So those are very, very important theoretical questions.
I think I just want to say, we did an interview, I think 2 years ago, with a researcher called Orsa Tath, and I think he's working on quantum information theory, because a lot of what he was talking about was like theoretically what would happen, and it was cryptography as well. So I'm going to just add this in the show notes. It is a slightly relevant episode to listen to as well. But yeah, sorry, keep going. So your particular
work is more on the practical side of things. How do you build this? And especially, I'm interested in the technologies that would enable building this in a very scalable way in the future. You can think about it like computers initially, starting with vacuum tubes and then eventually switching into this integrated, first like discrete transistors, discovery from Bell Labs, and then going into integrated chip scale platform. So how do we build something that is truly, scalable, but still offers all of these quantum mechanical properties, entanglement, and so on, and something that we can build on a chip scale and use light and electricity, microwaves to control quantum entanglement and do quantum computing potentially and quantum simulation, in addition to quantum sensing and networking, where these platforms are already used. They are state of the art, right? So people already use these impurities in diamond as leading platforms for sensing and networking. So that's what I'm interested in. And we do make things and we measure them in the lab. Design is a very important part of this, because I said there is a lot of photonics, but this is a different kind of photonics. Photonics that we can use in optical communications can be lossy. It's okay even if you lose 50% of photons. You just crank up your laser and you send your pulses and you can still stream your Netflix videos at home. It's fine. But, in quantum applications, we can't afford so much losses. So we have to design things differently. And we sometimes need new types of components, right, that would simply just produce this better interaction for qubits. And this inverse design that we were mentioning earlier on was born out of that need to do things in a much better way than we're normally doing it in photonics. And of course, now people are very interested in it also in photonics, but again, the pressing need to do designs in a better way really came out of the quantum research that we've been doing.
When you say better, like what are you optimizing for with this?
We're often optimizing for footprint, for efficiency. I mentioned, in traditional optical communication systems, if you go to a foundry that makes chips for photonics, they would have something called coupler that would use to couple your optical fiber that can bring optical signals long distance onto your optical chip that would do some sort of processing there, maybe communicating to information between different electronic pieces on your chip, right? And, in classical communication systems, it's okay that coupling element loses 50% of the photons, right? But when we want to design things, we want that to basically not lose photons because information is encoded even in state of individual photons sometimes, right? So we are trying to improve efficiency, bring it as close to 100% as possible for couplers. We don't want to lose any photons when we are doing some sort of, routing of photons down the chip between different qubits, because again, information about some stationary qubit is encoded in state of that photon. And if we lose it, then we have to repeat everything. Then we can't scale things up or do whatever processing we're doing.
Are you also trying to make in terms of the actual hardware, like the chip design, are you trying to make that something accessible? I'm just sort of curious, how close to industry is this? Are you trying to make something cheap and usable, or is it still kind of in the realm of we're trying to make this work?
Yeah, usable, definitely. Cheap, I don't think that anybody worries about that.
Maybe we're not there yet then. Maybe we're not on the cheap side
Nobody's
yet.
there yet. Cheap,
Okay,
this is an expensive hobby. But everyone...
It requires a small nanofabrication facility at Stanford.
Okay.
Yeah, every approach is expensive, right? And there is no cheap quantum processing platform. Everything is super expensive. Everyone uses fridges. So we're working on things, again, all the platforms are expensive, require very expensive equipment, lasers, dilution refrigerators, fabrication, that's all very expensive. But we are trying to put things onto chip scale, which I feel eventually in the longer term would be more scalable and in some way more accessible, because we can pack a lot of qubits into the footprint of the chip, and we can also benefit from decades of development in semiconductor integration and processing, although we're using a little bit different materials.
Is there any point where you're trying to make things work over wider spaces or with more nodes? Is there ever...
Yes, definitely for quantum networking, that's exactly what you want to do.
Yeah.
Because you need to build nodes every, let's say, 50 miles from west to east coast if you're building quantum repeater. And then in each of these nodes, you would have some of these entangled objects that you would distribute so that you can eventually do secure quantum communication between east and west coast. You can't just send entangled photons over 2,000 miles because it won't work, because attenuation lengths of fibers are maybe 50 miles and you will lose them, right? And that's why quantum cryptography systems are generally short to distance. But then you can maybe build, and in the context of quantum computing, this is also important because maybe on a single chip, for example, what the Google is doing, they can have 100 qubits that are doing something, but they're also running into problems of bringing in control wires into one dilution refrigerator. So they want to shift into the idea of distributed quantum computing. We already have that in classical computing. But then how do you connect these multiple bridges and build quantum network of quantum processors? Because you also have to kind of distribute entanglement in that case as you do in a quantum network. And that's also the approach, the goal towards which we're going. Although, at the moment, we don't have limitations in terms of how many qubits we can pack on a single chip. I mean, eventually maybe we will have, but we're not there yet. So there are limits coming from for different reasons in different platforms that are not there yet for the platform where we're going, because we're talking about kind of putting a single atomic impurity at some position on a chip. And if chip is 4 or 6 inches, you can pack billions and billions of them there, right?
I want to kind of go back to the pictures that we painted a little while ago, like the chips and the diamond with like light photons basically moving through it in a specific pattern, activating the different qubits. I just sort of want to understand, like, is this a kind of closed quantum system where the things you're communicating between are these different qubits within this? Or does it communicate with something, with like a duplication of itself somewhere else?
It could be a closed quantum system that you initialize and it's doing some sort of simulation or running some quantum algorithm. And at the end, you just read out the state of that system and you obtain some measurement result, which provides information about whatever you are doing with the system. But of course, you want it isolated from the environment as much as possible so that it doesn't lose those quantum mechanical properties. But it could also be a network of systems that are communicating together because they're sharing this entanglement as they would just in a simple quantum communication network. But it's basically a network of quantum processors where you can achieve additional capability by basically distributing some quantum algorithm over multiple nodes, right? That you are able to implement. And there are also other ideas, and people are also thinking about distributed networks of quantum sensors. In some cases, you can obtain advantage there relative to just localized sensors. So it could be localized to a chip. It could be a system of chips that are connected within one lab. It could also be a system of chips that are connected like over longer distance, especially if you would like to do communication.
Yeah, interesting.
So one of the things I've been hearing about lately, especially in the side of quantum technologies, but not so much on the side of quantum computing, has been this notion of quantum sensors. And yeah, I've heard this idea of quantum GPS, which I have no idea what it is, by the way, no clue of how familiar you are with it. But also similarly, like things like quantum Hall effect sensing and all this stuff. And it seems that this is very much in the realm of things that are coming in the near future. But like, what are the current like sensing technologies enabled by like quantum technologies now that like are not so obvious,
Yeah. First, important thing to mention is a lot of technologies that have existed for decades are quantum mechanical in nature, including GPS, which is based on atomic physics systems. Also timekeeping.
Because of the clocks, right? If I recall correctly.
Exactly. All of the timekeeping, precision, clocks are also based on atomic physics systems and atomic transitions that are quantum mechanical in nature. But there are new things that are emerging, right? For example, magnetometers, right? So one of these qubits that I was talking about was single impurity, one single atom of nitrogen in a block of diamond can be used to measure with very high sensitivity magnetic fields and with also very high resolution, in space, because it's just a single atom, which is, atomic resolution, sub-nanometer resolution. So those are interesting ideas that are emerging. And again, here you don't need to build entanglement of millions of these. You can still use one of them for something useful, and you read out its state optically. So people are thinking of using them for various measurements in medicine, right? EKG or, whatever you produce some sort of magnetic fields that could be sensed with this.
Interesting. There's a word that's sometimes used, and I think after what we've talked about, this actually makes a lot more sense, but it's teleportation. And I'm wondering, when we kind of going back to the cryptography side of things, like that intersection, is it the teleportation that is the sort of system where you can start to send secrets, or is that something else?
So teleportation is a very interesting concept. So kind of going back to Star Trek.
My fave.
Teleportation. Yeah. We all, grew up thinking, well, you can teleport things and travels faster than speed of light, and you can teleport humans. Teleportation, well, there are a few caveats here. We can't teleport humans.
Not organic matter yet.
I know, maybe eventually. Not organic. Second, it's not faster than speed of light, because when you look at teleportation protocols, you can teleport the state of a quantum mechanical object from one position to another position, right? You can kind of replicate it at another position, but you're destroying the state at the original position. So if something goes wrong in the teleportation process, you're losing the object at the original position, and you're not recreating it at the final position, because there is something called no cloning theorem in quantum mechanics, which says you can prove that you can't clone quantum mechanical objects. So you can replicate their state at another position while this kind of affecting their original state, destroying it. But the resource, again, that you use to perform teleportation is entanglement, right? So without entanglement, you can't do teleportation. In order to teleport object from state A to state B, you first have to distribute entanglement between these 2 points. And not just that, in the protocol, you also need to use classical line, like a phone line, to transmit some information in order to perform teleportation accurately, which means that the process is limited to speed of light.
And it's limited to existing technologies then? Or are you using a separate type of quantum thing to make that message?
You are using quantum entanglement. So whatever you would like to teleport, right? If you would like to teleport state of one qubit from one position to another, I mean, you need a resource to do that, which is you need some entangled qubits between two states, right? So let's say I have something that I would like to teleport, right? Like a state of some photon. In order to do that, I would also need entangled photon pair as a resource between my position and, let's say, your position. And then we go through that some protocol, we're doing some measurements, we're doing something, we're calling each other. And boom, at the end of this, you have that photon in exactly the same state as my original photon, right? Because we shared the pair. So your half of that entangled pair would be exactly in that same state, right, as my original photon, but my original photon would not be in that state anymore, right?
Okay.
So you need entanglement again as a resource. And we started this discussion by saying, well, all of these, beautiful things that you can do in quantum technologies all require the same ingredient, quantum mechanical entanglement. And that's true also for quantum teleportation. Teleportation also needs entanglement.
And here's kind of going back to what I was saying with like a encrypted message or something, sending something like that, sort of like using this for cryptography.
Yeah.
Does it use teleportation, or is teleportation it's just a state teleportation, so you would never be able to send info?
Yeah. It's just a state teleportation. I mean, you don't get any info unless when you're performing teleportation protocol, you know that the replicated state of something that I had, quantum mechanical state of something. But to transmit information, there are different types of protocols. There are many different protocols. I mean, they're pretty old. They're 20, 40 years old, right? 1984 is BB84, BBM92. Those are short for Bennett, Brasser, Mermin. Some of them occurred in IBM and so on. Then, they were proposed a long time ago, also demonstrated a long time ago, 30 years ago for the first time, but over short distances. The new thing is long-distance entanglement distribution that you would need as a resource in order to scale this quantum communication to longer distances. So while, I think there are a lot of similar steps in teleportation protocols and all of these quantum communication algorithms or protocols, they're different protocols consisting of the same operations that you're performing along the way.
I see.
Right? Because you have to, in order to transmit a message securely between us, right, we need to extract some information from whatever we're transmitting. If you just have one object that is the same as the object that I had, I mean, you are not really extracting any information from that, right?
Yeah. But what if you had something, each of you had something, and it was the teleportation that unlocked those things? Did they ever explore that? Where it's like, I think, Guillermo, I think you had sort of mentioned, or this may be before we started recording, where it was like a type of randomness or something where it matched a similar type of randomness. Like, is there something where you can almost like have the same message on either side and it like unlocks something?
So the no cloning theorem actually is very annoying.
Oh.
I mean, it's very cool because it's like the reason why all of this works, but like very annoying, right? Because this is the no cloning theorem is the reason why, like when you two, did this thing like 45 minutes ago where you like spread randomness, is like why I can't go in and like copy
the
qubits and like get your randomness.
Okay.
Right. So But the fundamental like construction there is that like the data is random. Like you cannot get around that. Like the data for you two to share the same secret, right? That is copied in two different places. You cannot transmit information using that data, except for the fact that you both know you have some random string that is the same. But it has to be a random string. You cannot avoid that.
Yeah, but with that, can you do something on either side?
Of course.
Then?
Yeah. So shared randomness lets you do all sorts of crazy nonsense. For example, cryptography.
Yeah.
Right? If you both share a secret, even if it's random, in fact, ideally, if it's random, then of course you can use it as your private key, which you both now share. And you know nobody has snooped into because you performed this cool check.
Yeah.
Right? The difference here with teleportation is that you're not performing any cloning because by construction you cannot do it. Like you can't like take the qubit and like make another qubit just like it.
I see.
Like you have to destroy, like in some sense, in order to construct the second qubit, you have to destroy the first qubit.
Got it.
Which is like weird and philosophical.
No, I understand. I think I'm mixing it up. I think I thought the teleportation was that sort of randomness being existing in two places.
So those are quantum communication protocols.
That's quantum communication.
Yes.
Got it.
Quantum communication protocols where you're producing some random stream of bits, and you know at the end of the protocol that it's the same between two parties, and then you can use it as a secure key, one-time pad or secure key, right?
That's so cool.
Yeah.
Okay, I think I fully understand also my confusion. I had thought the teleportation was that. It's not. It's this quantum communication.
The teleportation is still super useful, right? For example, connecting different quantum processors, you go through some quantum teleportation protocol. So it's not like it's just a concept from Star Trek that's not useful. It's super useful, right? It's just that, and it's the same sequence of operations you use in all of these, but just protocols are all a bit different because eventually in communication, you want to produce some stream of bits that you know is identical between you and Guillermo, right? And then you can use it for your cryptography. Yeah.
We just went over that case of the randomness, but is there any other ways that quantum communication, quantum systems are being used to like share secrets, to do something that's sort of more edging onto the cryptography side of things?
On the cryptography side of things, I mean, there is, that's a relatively simple thing, and there are already commercial systems for this, random number generators, right? I guess people, because in classical computers, it's pseudo-random number that we're generating. Yeah. So if you would truly like to generate random numbers, then you can use a very simple quantum mechanical system consisting of a single qubit, right? Because when you perform measurement, it's truly in a 50% probability of being heads up or heads down, right? If it's a quantum mechanical object. So it's not biased in any way. And if people want to have really a truly random number generator, then they can use quantum mechanical system, right? And it's a simple quantum mechanical system. That's one additional example, right, of a simple quantum mechanical system that could be used for something useful.
Cool. With what you've built today, like, are there ways for people outside of the lab to actually engage with your work? Like, are there things that people can, like, are there libraries? Are there things that people can play with?
Yeah, we have open source softwares. I mean, we were talking about photonics inverse design. And if people go to GitHub, my lab's website, Stanford Nanoscale Quantum Photonics Group, NQP, or GitHub SPINS Photonics. SPINS is short for Stanford Photonics Inverse Design Software, but now my former students started a company focusing on that. But we have open source softwares there, and Guillermo was contributing to some of this when he was at Stanford on the bounds.
Way back in the day.
Way back in the day. But if you would like to play with designing interesting photonic devices, I mean, actually, you are not doing much. You don't even need to know photonics or electromagnetics to do that. You just define the problem, you want to say I want my light from the input to kind of change in a certain way at the output, and this is a black box, and basically then this software searches the whole parameter space and designs these structures that would really do that for you. And, if someone wants to make them in a foundry, then they can take this pattern and send to a foundry or go make things themselves that would basically do this processing on light. Yeah. And these are open source. People can download, use them on Google Colab or, their GPUs, gaming GPUs, or if they have, H100s, they can use them.
Oh, that'd be cool.
Very nice.
Those are hard to get nowadays,
Yeah, we have them now at Stanford, actually. Maybe it's time for you to get back.
Yeah, maybe I should go back. What am I even doing here?
Yeah.
Yelena, thank you so much for coming on the show and sharing with us all of this information about quantum engineering, quantum technologies, photonic chips, the creation of these chips, the modeling. It's been wonderful to get a chance to ask you all of these questions. I've had lots of questions about this field. So yeah, thank you so much.
Thank you. My pleasure. Thanks for inviting me.
Thank you so much. Always lovely to see you again.
Oh, I know.
It has been a little bit too long.
Yeah. Stop by sometime. We should grab coffee or something.
Yeah.
Chat. Yes.
If you're not careful, I will take you up on the invite. You're going to have to deal with me for like
you're
another
always
hour.
welcome. Yeah, of course, you're always welcome. Yeah.
Thank you, Guillermo, for introducing us to Yelena. Thank you so much for that.
Of course.
And for joining us, our co-host today. I want to say thank you to the podcast team, Rachel, Henrik, and Tanya, and to our listeners. Thanks for listening.